All right, let's talk about why iterators got it all wrong and what we should use instead. Now, iterators have been part of C++ since the Stone Age, right? Well, maybe since, I don't know, the STL library, somewhere in the 90s. Not quite the Stone Age, but for C++, it's the Stone Age. And they are modeled after pointers, right? So they are really a concept that was built from kind of the bottom up. People had pointers, and then they needed to have some generalized pointers, and then they said, well, okay, let's call them iterators, and that will be fine. And maybe that's where their shortcomings come from, but we'll get to it. Now, D thought this whole idea about iterators is stupid. We're going to do ranges, and we're only going to do ranges. And everything is a range, which in my eyes is weird, because if you have 3 positions in your range, right, 1, 2, 3, because you have an algorithm that deals in 3 positions, it's kind of weird to say, well, I'm going to pair arbitrarily 2 of them and put them into a range, because I mean you'll store redundant information, right? Which is kind of weird. So I don't want to do away with the iterators, or at least with that general idea. I don't want to make everything ranges, just like D, and C++ agrees. I mean, the committee says, okay, we're going to stick to iterators. What can iterators be? They can be elements of a range. So you got a range, 3, 2, 1, 3, and you say min element, and pretty clearly when you run min element on that range here, then you would get an element back, which is this 1, and clearly this 1 is an element. It's this 1. Well, why am I stressing that so much? Because they can also be borders. So here you have a vector 0, 0, 1, 1, and you say upper bound of 0, which is the end of the range that is 0. And here we don't really designate a particular element. We designate a border between elements, between the 0 and the 1. Right there is where it ends, where our zeros end. This is actually the way this is coded is we point to the element that is right after the border. That's the convention. That's how we do it. Now with C++, well, 11 it started. We had the range-based for loop, and now Eric Niebler is actually slowly introducing the concept of ranges. And what is a range? Well, a range, in the committee's eyes at least, is anything basically that has iterators, right? Where you can write a range-based for loop, and the range-based for loop is based on iterators. They're really separating into 2 different things. One is well known to us, which are containers. They've been also with us for a long time. A vector, a list, a set. They all own their elements. When you copy the container, you are also copying the elements. And that copying of the elements, of course, takes O of n time, because you have to copy n elements. And they have deep constants. If you have a const container, you can't mutate the elements. Seems all pretty natural until we look at what else we have. And we have views. What are views? Well, views are kind of the opposite of containers. They don't own the elements, they only reference the elements. When you copy them, you don't copy the elements, you only copy a reference. And they have shallow constness. If the view is actually const, then that doesn't necessarily imply that you cannot mutate the element. It's like, well, this is a strange beast, right? Where do we have that? Well, we pretty much have it everywhere in the STL. They just are encoded as iterator pairs. Wherever you're passing an iterator pair, the idea is that you are passing a view to a container or another view. So you're passing a range, and that range is a view. And yes, the const iterator, as everyone knows, if you have a vector const iterator, if you cannot mutate the const iterator, that doesn't mean or if you have a mutable const iterator, that doesn't mean you can mutate the elements. You still have a const iterator. Same with if you have an iterator and the iterator itself is const, that doesn't mean you can't mutate the elements. You still can. Okay, so this is where it all comes from. You have pairs of iterators having being a view. And that's the kind of the simplest view you can have, are these pairs of iterators. Why would you like to have something like that? Well, because it makes the code much less verbose if you are combining these iterator pairs into a single object and call it a view. Here's an example. First, we write this with iterators. You have a sit vector. Now you sort the vector, and you say vec begin and vec end. And then you say, okay, we erase, vector erase, and then you have to run std unique, vec begin, vec end, and at the end, you run vec end. Okay. I'm sure people are pretty familiar with that kind of code. You sort a vector, and then you erase the duplicate elements, right? That's the standard way how to do it. But the code is wrong. Or at least not quite correct, not quite nice. What's wrong with this piece of code? Who sees the problem? You erase the elements by first sorting, and then you're removing the duplicates. What is that? Yeah, the parentheses are missing. Maybe. That's fine. That's not what I meant. Okay. In order for this to work, the sort and the std unique have to play together. The sorting is basically lumping the things together, the duplicates, and the erasing then, or the unique, then kind of compacts, right? So they have to do the same thing. They have to run on the same predicate, but these don't. Std sort runs on the less operator, std unique runs on the equal operator. This is okay for an int, but it may not be okay for other types. And if I write a general library function that is supposed to work under all circumstances, I have to commit to something, and I'm going to commit to the less operator. So this is another reason why you should write it really this way, where actually this way it's written with unique in place, replicating the mistake from here, but the way it should be written is probably there is a sort unique in place function in our library that you can actually download from the web, and it actually does the right thing. It turns around the less operator to do the unique operation. You want basically a not less operator to do the unique operation. And then it's correct, then it really relies on the less operator under all circumstances. Okay. Now there are more interesting views than just these iterator pairs. There are range adapters. They are not yet in the standard, they're not even proposed for the standard. They are, though, in Eric Niebler's range library, and there are also in our range library that you can download. And these range adapters, what do they do? Here's a motivating example. You have a vector that is 0, 0, 1, 1, and you find in that vector an element 0, okay? And you return where you found that value. That's somewhere here in the first element. Now, let's say instead of a vector int, you have a vector of pairs. Now, in order to find the element with the 0 here, you have to write this. You write find if, and then you put in a lambda that does the comparison on the first element. Semantically, these two things are doing quite similar things. They're finding zeros. But they're pretty unrelated in syntax. We're using a different function, and we are describing the comparison in a different way. Here we simply plug in the 0. Here we write the equality. Okay, so that's not nice, that similar things are expressed in such different ways. And the reason that this is happening is that this lambda here is really doing two things at once. It's expressing the projection, the A first, and it's also expressing the comparison against 0. And we would like to pull these two things apart. So we can use a similar syntax for both of these cases. Enter the transform iterator. So here's again how we write it for a pair with a lambda. And here's how we separate the projection and the search criterion. We have a function transform that takes a vector and takes, again, a functor that does the projection. It just does the projection on first. And it returns a view that has transformed the vector. The view only references the vector. This is not copying the vector, and just by doing this, you are not doing anything. You are just producing an object that if you start querying elements from it, would start doing something, would actually start querying elements. This is lazy. This is merely a view, a pair of glasses that you put on through which to see the vector. And only when you actually start going through it, it will actually start pulling elements from the vector. And now what you can do right is you first get this kind of object, transform vec mem from int char first, and then you find the first element, and you can see that the find now looks exactly the same. You have a find trans 0, right? So just like before, you had a find vec 0. So you just encapsulated your projection into this transform. Okay. Now, let's take a look at this. You have the vector again, and you do it the old-fashioned way with the projection and the comparison lumped together in this lambda. And after you did the find if, you do second, and of course you get an A here, right? So first you get an element, which is here, and second, and the second of that pair right here is the A. So that's what you're getting. Now let's try the same thing here. Okay, you have this transform that we built, and now you say find transform 0 second. What do you get? Right, because this is a view on ints. It's not a view on pairs anymore. We threw the part of the pair away. So basically what we want now is we want a function that goes back to the original iterator. And all these transforms always have a base that basically goes from the iterator back to the actual that wraps off the transform from the iterator. Okay, and then you can write, and indeed you can write this, find transform 0 base second, and then you get your A. Okay, so as a picture, it looks like this. You got your vector here, you project it up into your transform, and your base brings you back down to the 0A, from the 0 to the 0A. So you went up. Now this is the view of ints, and then you go back down to the vector of pairs. Okay. Now the find returns an iterator in the role of an element. With find, we find the first element that has a certain property, which is arguably not a border, but it's an element. And when you say base, then you would like to preserve the identity of this element. This seems to be very natural and without doubt that you want to do this. It's probably something you would never question. But we'll see that it will get difficult later on. So here you're pointing basically to the first element in your vector, and when you go back to your pairs with base, you again get the first element. So you preserve the identity. That 0 here came from that element from filtering this element there. So let's go to upper bound. Upper bound returns an iterator in role of a border. And the same base has to preserve the identity of the border. So we are sitting down here, going up there, filtering our vector. We found now a border, which is right here in that filtered vector. And we would like to project it down into a border right here. Now, if we use base on the iterator is always after the border, the right thing happens. We'll get the iterator that was after the border here is still the iterator that is after the desired border here. So everything is good. You can already see from the example, it won't stay that way. Let's look at the filter. Filter and transform are probably the really important views. Many of the applications, if you look through our code, we use this everywhere, are really transform and filter. What does filter do? Well, it restricts the container or whatever is the underlying range to the elements that fulfill a certain filter criterion. So here, for example, we pick the ones where the p second is b. Okay, so and what we get out is the element here which has a b and the element there is a b. So 0b, 1b. So here we now do first, a little bit bugged here by my cursor. So let's apply this. We first do the transform, or we actually did the filter, now we do the transform. And then we do find trans 0 base base. Okay? So we first did a filter, then a transform. So we had these pairs, then we go up here, now we have two pairs, we got filtered. Now we have two numbers, 0 and 1. And now we run our find, which finds us this element, and we go back down. And find returns an iterator and roll of the element. Of course, the result would be different if we hadn't filtered, because then the 0 would be right here. But that's too much to expect. I mean, that's kind of natural. We picked an element, and we preserved its identity. So this element here, this 0, came from the 0b here. So it's just natural that if we call base base, we will still get something in the original sequence that agrees with the identity of this element. So it's all okay. The base must preserve the identity of the element. Of course, now we try the same thing with upper bound. So we have an upper bound. When we find the upper bound of 0, we'll find in that filtered range here, we find a boundary which sits there between the 0 and the 1. Now we do base once. Now we still have a boundary that sits between the 0b and the 1b. So far, so good. But you can see now it gets hard, because the iterator will point now to the 1b element down here. But our boundary is really not well defined. If you're writing code like this, you very likely made a mistake, because the boundary was defined without the elements in between. You don't know what happened with the elements in between, and now basically you fill them back in. So what is the algorithm going to return to you? Is it going to return to you this boundary or that boundary? It doesn't know where to put this element, because the element wasn't in the sequence where we actually determined the boundary. So it's not a disaster, but it's becoming strange because you are not warned of a potential mistake that you made. There's just no equivalent of the boundary in the filtered sequence if you go to the unfiltered sequence. So in the best of all cases, this shouldn't compile. The answer could be, well, then don't do it. Right? You shot yourself in the foot, well, that's your fault. This is kind of a good tradition of C++. If you shoot yourself in the foot, that's your problem. Okay, so far so good. Let's go to the reverse adapter. That's also a very natural thing, right? It just turns the view around. And we play the same game. We do a transform, and we do a find, and we say, now we found this first element that has a 0. Now this thing is reversed, right? And we do base, which undoes the transform. We're now here. And then do we base again. And we should be projecting to this element, because, I mean, this is the identity that we are looking for. The 0b is there. We found it. Well, we want to know where it is in the original sequence. There it is. All good. Now we do this with something that returns a border, lower bound. The lower bound of 0 is here. It's this 0. The lower bound here is the 0b. Still, this is an iterator. Goes all the way through, and it returns us this element. The problem is, this is not the right border. If we are interpreting this iterator here as a border, it's right after the border we are looking for, and we are then it's all fine, and when we go to the unfiltered sequence, we still have the right border. But what we would like to do now, if we undo the reversing, is we would like to have a border that sits between the 0 and the 1. I mean, we kind of chop this thing in the middle right here. Now reverse it. Now we unreverse it. Where do we chop it? Well, we chop it still. We should be chopping it still in the middle. If we're talking about borders, it's unambiguous what the result should be. But the same base cannot give us both. We can't have a base that does the right thing for elements and the right thing for borders, because they have to give two different results. This cannot work. Now, why is that? Why is the reverse adapter so strange? How does it look under the hood? And I want to do this so that it's not like, yeah, in theory, this is all nice what we are doing, but you know, how does it really look in practice? Where does this problem come from? And I want you to understand where the problem comes from. Let's look at how a reverse iterator is implemented. Well, incrementing, we have a reverse adapter here, and it has an iterator. So this is that's where the meat of the stuff is happening. The begin is implemented as returning the end. The end is implemented as returning the begin. And going forward in the iterator that is reversed is going backward in the original iterator and vice versa. No surprise there, right? Interesting is the dereference operator, because it subtracts 1. It goes to the previous iterator before dereferencing. And, well, why does it do that? Well, the iterator at begin, the reverse iterator at begin, internally, here it is, begin, stores base end, right? And it can be dereferenced, because begin iterators can be dereferenced. Now, it must return the last element of the underlying sequence, which is base end minus 1, as we all know. Now, the iterator at end stores base begin. And subtracting would be disastrous because we are ending up somewhere in front of the range. Well, but it never gets dereferenced. Dereferencing an end iterator is undefined behavior. So this never happens. So if if we decrement the end iterator to end minus 1, then the base begin becomes base begin plus 1. Then we subtract again doing dereferencing, so base begin plus 1 minus 1, and that's again base begin is exactly what we want. So when you dereference end minus 1, you want to get begin. Okay, so the point here is the element after the border in a reverse sequence is the element before the border in the original sequence, which is why this is basically why it cannot work. We have this convention that we are talking about borders as the iterator after the border, but that very iterator after the border becomes the iterator before the border in the original sequence. So now I describe the problem. There's a problem with the filter iterator, there's a problem with the reverse iterator, and arguably the reverse iterator one is pretty bad. I want to look at how big is the scope of that problem where iterators just don't do it anymore. So when the adapter changes the order of elements, okay, like here, it's completely jumbled. You go A, B, C, D, and it completely jumbles it up. Like you may have a virtual sorting algorithm or something like that. It gives you iterators which are in a completely different order than the original ones. The base of element is in general well defined. You can still find the original element, it's all good. The base of border of the border is in general completely undefined, because I mean you jumbled all the iterators. What's before and what's after is meaningless in the original sequence. So this should really not compile in this case. Example is the sort adapter. Now the reverse adapter is a very exceptional thing, because everything changes size. Borders still have a meaning. The base of a border is well defined, but it's different from the base of the element. This is the case that we just had. Now, when we have an adapter that removes elements, then the elements may collapse into the border, So the base of elements is still well defined. It's all good. For every element here, we can find a corresponding element in the original sequence. But the base of border is ambiguous. We can't do, if we get a border out, we can't go from the border of the smaller range to the border of the bigger range, because there are certain elements that just weren't there and we don't know what to do with our border. It happens with a filter, but there are other things that remove elements. Sorted intersection, sorted difference. They also remove elements from a range. So there you would have the same problem. Now let's have an adapter that adds elements. Okay, where's the situation there? Well, an adapter adding elements is kind of a bit hard to find, but sorted union would be one. So essentially, you just you merge your range that you want to go back to with another range, another sorted range, and you kind of interleave the two. And then it will add elements. And in this case, you don't have any problem with borders. I mean, any border you have here just stays a fine border in the original sequence, right? Because you're just removing elements. But, well, if you pick an element, you can't call the base on elements without any trouble, because the element that you're pointing to that you want to call base on may just not be there. So ideally, you want the base in terms of borders work, but in terms of elements, it shouldn't compile. So, what do we do for this particular case? I could say, well, you know, the base function is a bad function. Really, what we should be having is two functions, border base and element base, and that's a very small change. We just say instead of base, we have two bases, essentially, and the problem is solved, right? But there is no safety against you choosing the wrong thing. And here's what I would find a whole lot better. There are really two different concepts. Iterators are the wrong abstraction. We have borders and we have elements, and they should not be the same thing. We shouldn't have iterators. Iterators are at the wrong level of abstraction. They're pointers. But we're not interested in pointers. We want to write meaningful programs that have semantics. And for that, we should have a better abstraction that separates the two concepts of border and element. And then base would always do the right thing. And the question really is, do iterators in a real-world code base fall into the two concepts, either border or element? Do they? Well, you would have to analyze a pretty big code base to find out whether you can make this distinction. And it doesn't really help if you don't really know what to pick, because it doesn't have any, you're looking at something and you don't really know what it is, right? So you should have done this exercise once. We did. So we have 1 million lines of code, and we found out, well, for most iterators, whether they are borders or elements. And you can do it. There's a find. Find, we went through all the functions, what they return, all the algorithms, what they return, and looked at what kind of thing are they. Are they meaning borders or are they meaning elements in the context of our code? What kind of concept would I apply to them? What kind of type would I apply to them? Would I call them border or would I call them element? So, find has 201 times we were interested in only a single match in terms of find. So it was assured that in these cases, the element would only be found once. And in this situation, of course, it is pretty clear that it is an element role pretty much all the time. Because you are not talking about a beginning and an end. You only have a single one in your sequence that fulfills the criterion. So it's that one that you're talking about. So we found one border role, one iterator incremented to actually get the border after. So it's nice and symmetric. You have the border before, the border after. That's what we were interested in. But all the others, 199, were the element that we wanted to talk about. Okay, 98 are first match. Now, you can imagine that first match has more of a tendency to be in the border role, Because you're finding some first match. Maybe you are now interested in, for example, the prefix until that held that criterion did not hold. Okay? And in that case you would have found a border. Or you want to find the element. Well, in this case it was 7 border roll, 5 incremented to get the border afterwards, and all the other ones had the element roll. But there were quite a few more borders with first match than with single match. Find if, similar picture. 67 single matches, all element roll. 75 first matches, 3 borders. Lower bound. Well, it's actually surprising, but most of the time when you're using lower bound, you want to find an element. Really what you're implementing is binary search. You're looking for a particular element, and it was usually even a single match. 89 of the use cases out of all these were looking for a single match in basically a sorted container. You had a vector, it was sorted, and you want to find a particular element. And that's an element you're talking about. It's not a border you're talking about. 19 found the first match. They are all element roll. And you can see for these two, you need the predicate of the lower bound again. So you can see this quite clearly because you have to distinguish whether you found an element or whether you found no element. And in this case, it's clearly not a border because you have to you check this element again, whether it's really a match or whether it's simply something that is greater. So lower bound founds everything that is greater or equal, right? So you want in the second 2 cases, we wanted to find the equal one. Lower bound gave us something that's greater or equal. In the second 2 cases, we want to find the equal one. In the first 2 here, we didn't care. We wanted the border. Okay, upper bound. 24 total, 17 border roll, and 7 decremented to get the element before. So it's interesting that they actually got, no one got incremented. Because it doesn't make any sense. There's no meaning to, and the upper bound has no meaning for the element afterwards. That's not what you're looking at. What you're looking at is the range of elements, that the equal range, that is the lower bound here and the upper bound there. And it makes sense to go from the upper bound into the range you're looking for. But to go beyond the range, look at the element there, doesn't really do anything. And it's never happening. We are then looking at the border. So we found iterator instances can be pigeonholed into either borders or elements. And I mean, guys, iterators were ugly anyway, right? Who can explain to people that iterators point to the first element and beyond the last element? This is so asymmetric. This is so ugly. And I mean, if you have a newbie in C++, I mean, you try to dereference the end. Well, end must be symmetric to begin, right? If you can dereference begin, why can't you dereference end? What kind of, this is stupid, right? This is much nicer. Now you have a begin, that's at the beginning of the range. And you have an end, that is at the end of the range. What if you dereference them? Well, you can't. You're pointing at a border, for God's sake. You can't dereference borders, right? You can dereference elements, and they are in between, but they're a different beast. So, and here's another ugliness. Find returns end if it didn't find anything. Well, most of the time, this makes no sense. I'm writing something like this, auto it find, and then if it unequals end, then something. Well, what's this end here? Why do I need end range? Why do I need the range again to test this it? I mean, there were null pointers before, and now we have always these end iterators lying around somewhere. It's terrible, so ugly, right? What we want is yeah, you have to mention the range twice, and you cannot write it inline. It's bad. You want to write this. If auto it equals find, then do something. We found it, good, done. So, and this is an element. And an element should have a null value, right? If element, then the magic value is null, just like a null pointer. If you have a base, you basically have a no element, which is null, and that should be returned by the find function if it didn't find anything. We've done it in our code base. Works very well. So here's the border concept. So These are all these lines here. They're borders. Here. They are like iterators, like today's iterators. And under the hood, if you look underneath, yes, it's still an iterator, of course. You just name it differently. It cannot be dereferenced. And if not at its begin, then it has an element before and an element after. So you can symmetrically look either before the border or after the border, depending. And of course, you can't do that for the begin and the end, but it's still all symmetric. And the range begin and end, the std begin, std end, are of course borders, because they are at the beginning and the end of the range, of the whole range of our container. And actually all the iterators going into our algorithm are borders. They are either the begin or the end of the input range that you pass to the algorithm. There are no elements anywhere to be found. Now, all the output iterators, I don't like output iterators. I think they will go away at some point. But they're also borders, because they basically describe the end of where you're writing. And here it's full already, or from your point of view, here it's full already, and we are stepping forward. And the output iterator always describes where you ended to write, and where you will, and after, before you already wrote, and afterwards you will still write. The iterators return from algorithm, well, that depends on the algorithm. Their return iterators are borders for the functions. I have them all here. I went through the STL, decided, okay, how do I categorize them? Is it a border? Is it an element? And they are clearly all borders. So mismatch is the end of the matching prefix. The search, begin of a matching range, lower bound, upper bound, we had them all. Equal range, clearly. Partition point chops the range in two, so it's clearly also a border. And unique returns the end of the compacted range. It compacts everything and then returns the end of that.
So remove.
What is that?
Remove also.
A remove. What does remove do?
It reorders elements so that the elements which do not match are at the end. So
they're compacted. Yes, remove would also be a border. It's very similar to unique, I guess. I don't have unique. No, I have unique in here. Okay. Element concept. These are the elements right there, these. They're like iterators, but they're never end, and they cannot plus the last element. They have to stay elements. And they, of course, have symmetric to the element, to the border, which has an element before. The element has a border before and a border after. And there are algorithms, actually, that return elements. They're few and far between, but at least the max and the min element, this pretty clearly is an element. It's not a border, because it has a property with respect to all the other elements in your range. Then I would say we have a range of elements to get all the elements inside some border. So you plug some range in, you get a range of elements, and it will actually, when you iterate through it, it will give you elements. So this is just to get this straight. This is not iterating over the values of the range. This is giving you here, passing in iterators. It turns, in the old speak, iterators into iterators. You plug two iterators, which are borders, in, and you get all the elements, which are iterators, in the middle out. Okay, this is what this does. So, and we already said it, we would like to make the element nullable. This is compatible with pointers. The pointers satisfy the element concept, right? So, because they can be null. And the element should be contextually convertible to bool. So you can write something like if auto it equals find, blah, blah, blah. And the null state, just like before with the pointers, can be reached through value initialization. If you write element, and this is an element type, then you'll get the null state. And the function returning an element, like for example find, they return null instead of end. So you can write this. Okay. So I would go one step further. I would say let programmers encode their intent even more. So we separated the find into several functions which would let you say something more specific about what you are finding, what you want to find. One is the find unique, right? This is quite frequent, that it's merely basically an optimization whether you start searching from the beginning or the end. Because you strongly expect only a single element. And you should say so in your code. Of course you can assert it at the end, or you can write a comment or whatever, but it would be much nicer if you could actually write this in your code. So I would recommend have a function find unique that lets you say that. And of course then there must be find first, find last, and trim left and trim right. Well, what does trim left and trim right do? How are they different from find first and find last? Well, they return borders. There you can say that really I'm interested in chopping off a prefix or a suffix from my range. And I don't want to find an element right now, so I'm getting a border returned. Other than that, I mean, the trim functions and the find function are very similar, even if they're used in a different way, but they really do the same or similar things.
What does underscore if mean?
You need to have, probably you will need a function, another function that allows you to put in a predicate. So there's a find and a find if. I wouldn't change that, right? So you have replicates of that thing, duplicates with if. Okay, lower bound. Again, terrible, right? We found out lower bound is not really used how it's supposed to be used, as to find a border. Most of the time, it's done for binary search, where you're looking for an element. Okay, why don't we have a binary find unique, a binary find first, a binary find last? They can return all elements, right? So why have this border, this lower bound thing, and then you have to check afterwards? Because here, if you don't find it, if your binary find unique fails, you get a null back. You don't get some iterator back that you don't know what to do with, right? So it does the extra check internally. And of course, you still have lower bound, your good old lower bound. You will use it a whole lot less. It returns a border. And remember, you can always use the border before, border after to convert elements to borders. And if you get a border, then you can use the element before or element after to convert the border into an element. So element to border, border to element is no problem at all. And yes, I said it, the unique functions assert that it's a single match. So we already had this, auto it find unique range. And it's nice because we only have to mention range once, but we want more, okay? We will introduce a template parameter to control the return value. So you can now say things like this. Return border, lower bound, return border gives you the border. All good. Lower bound return element doesn't give you anything, okay? That doesn't compile. It would be strange. But there is a lower bound return take and return drop. So you basically chop off the range, and it gives the range back up to the point that is the border, or beyond the point, which is the border. You can either do the return take or return drop. And there's another template parameter that you plug in to say, oh, I want the elements after or the element before. So it does that extra function invocation for you. That's optional. If you don't like it, don't use it. It does have the advantage that if you are at the end or at the beginning and you do it, since they return elements, you get the null back. Okay, so if you're really looking for something after the border and it's not there, you get the null back. So now this was for borders. They all return. This was the lower bound that returns a border. Here's the same thing for elements. You can return element or null. You can also say, oh, return the element. Don't return null. I assert that I must find something, otherwise my program is ill-defined. I'm going to assert this away that I'll ever get a null back. Okay. And then, of course, there's the border before or after. And then you could say, well, what if there's this proved to be quite useful. What if if you don't find the element? You're looking for an element, you want the border afterwards. But what if you don't have an element? Then you say, oh, give me the beginning or give me the end, right? And that's quite frequently the outcome if you have that in your code. And here it's kind of the same things with the border variation of return take and return drop, because you can now say return take before, return take after, drop before, drop after. And here you can do the alternative. What if I didn't find the element? It's empty or all. Do you want an empty range or do you want all of it? Okay. So here's how it's implemented. We simply have these little structs, return take before empty, which basically say, okay, well, if I'm finding an element, then please pack it for me. Okay, and that's the iterator. That's the range. It gets forward. The range gets forwarded into it. We don't need it anymore in the actual find function, and then it does the take call. And here it's the case for I didn't find anything. That's how I implement it here. And and that was pretty much it. I started with iterators being modeled after pointers, which is a low-level machine concept, and I don't think it's been well thought out. Elements and borders have much stronger semantics. I would argue that already when we are programming, we're thinking in terms of elements and borders, so we really should write that down in our code. And it's needed for the correctness for important range functions, so now the need comes up to actually do something about it. We have a partial implementation, the thingscell range library, that you can look at, that you can actually also use. So the elements are nullable. We have these algorithm refinements. We have a return specifications, the template parameters. What we are still missing is we don't wrap all the borders, so they are not dereferenceable. And we also do not inhibit the conversion between elements and borders. So this is something we have to still do that requires even more wrapping of the STL functions. Thank you very much. And the last thing I have to say is we are hiring, but I guess you noticed this already from the posters. Thank you. And any questions? Go ahead.
My only question is when? When will this happen?
I don't know. I'm giving this talk also because I hope that people who have some influence in the standard committee will say, okay, this is a really good idea. Should I be that one? Yes, I probably should be, and I should do my community work. But yeah, we didn't quite get around to it. For us, we took the shortcut. We wrote our own library. We use it internally at thingscell. We think it's a good idea, but it's yeah. That's how far we got so far. And I'm promoting the concepts, that's why.
How easy or difficult is it to connect the code using these concepts, this library, into the traditional C++ code with the raw iterators?
So currently, of course, it's trivial because they are all interoperable anyway. We didn't put in the type safety yet. That was my still missing part down there. But that said, the natural way to do this would be to say, okay, iterators, when you're converting an iterator to a border or an iterator to an element, maybe that's explicitly convertible. You have to say, I now want the border, I want the element. Implicitly convertible, you can make the borders to elements, borders and elements to iterators all the time. So basically you have your top level iterators, and from that on you have borders and elements, right? And you can always make things more generic by casting up to the iterator. If you want to cast down basically to or whatever, how you're casting. But if you're casting to something more specific, then you probably would like to make this an explicit cast. But there you could pick and choose whatever you want. Right now we cast all the ways, and we don't. There's no real difference in our code base. But we do use all these all the return specifications, and I believe it would be relatively easy to fix up these things. It's not so hard because you really the semantics are clear at any point.
I wonder what's the principal difference between find unique and find first. I think find unique always will find the first element and return it. We should not search all the range and checks if any.
Do you know where the difference is? Do you know where the difference is?
What's the difference?
In your head. The difference is in your head, right? So Do we assert in debug whether there's no other element? Yes, we do. So we have instrumented the code. But in release, yes, we don't do the check because it takes too long. So, but I think that there is a principal difference in your thinking that you should encode. You shouldn't just throw this away, right? Because usually your program gets, you either has to deal with the fact that there are multiple of these and it's important, or most of the time you really assume that there's only a single one. And that's the majority of the cases in particular with binary search. I mean, usually you're finding this is a unique key, right? I mean, there's a std set and there's a std multiset, right? Are there any major differences between? I guess when you insert, maybe there are differences, yes. But you know, so I would make the distinction mainly for documentation purposes.
Combinatorial explosion to me. Did you think how to avoid the explosion? How to make this more decomposable?
We have them all now, and it's okay, and it's many. But if you think about it, there are not that many possible choices. There is always a border before, after, and then there is a range which combined with the begin and the end, and then you have the few things with elements before, element after. Border before the element, border after the element. So if you combine them all, you get a list of, I don't know, 25 or 20 or something.
You have 3 or 4 factors, each of them having 2 or 3 values. So
what is that? Say again?
We have 3 or 4 dimensions, each of them having 2 or 3 values, so it is up to 30. It is a combinatorial explosion to me.
Right, I mean, I think if you, I think we had I named them systematically, obviously. Unfortunately, it's not a complete orthogonal grid. It's not like you can fill all the holes. Certain combinations are not making sense. And if you want to write it, if you want to do a different syntax that basically decomposes these aspects, be my guest. I think that would be completely fine if someone comes up with something. I did this because we have something to put in our code. And you can always do a search and replace it with something else. If someone comes up with a different syntax, I'm not tied to that syntax by no means.
Have you thought about optional explicit option in element novel to get another of element?
Say again. Explicit options. Maybe we should. You mean like you just write just?
Yes, because sometimes you shouldn't have nullable elements. You should only return elements that are there.
Oh yes, but this is in the code. This is in there. There's a return element in there. It's very similar to what's the other thing that we here we write it right there. Return element. Oh, so you want a type for non-nullable elements. I think that's a good idea. We haven't done it, but probably in the direction of having everything compile time safety, that you can have some compile time safety. This is probably something that if you do it all the way, this should be done, yes. Yeah. What is that? If we did whether I have read it or whether I know about it, or compared it. Yes, there is a separate talk on it, which was actually maybe what was the talk that. Okay, I can tell you a few things which are important, and now it's just completely out of the top of my head. Eric decided. So, let's see. Okay, first thing. When you do have an R value, Eric decided not to aggregate the R value. So, if you have a transform of a function that returns a vector, that vector will You have a transform of a function that returns a vector. That vector will go out of scope after that statement, unless you store it somewhere. Eric decided that he is disallowing, the problem is that this transform will reference that vector. And when you store the transform in a variable, your vector goes out of scope, and you have a dangling pointer in your transform. That's bad. There are basically two ways to solve this. And Eric picked one and I picked another. Eric said, I disallow this. I just simply say R values are not to be transformed or are not to be adapted in general. I don't allow it. This is impractical, I find, in practice. Because you're writing long inline, you want to write relatively long inline expressions that you kind of want, you don't want to separate this into several variables, and you have to think up a name, and you have to you again have this situation that you have these pairs of stuff to ship around. One is your container that contains the elements, the other one is the adapter. I mean, you kind of are back into this iterator land where you have an iterator begin and an iterator end that always have to be shipped together around together. There you have the same thing. You kind of have you have to keep your vector alive somehow, right? And that's hard to do. So what we did is, if you get an R value into our adapters, they are aggregated. So the R value gets stored inside the adapter. It's no longer a view. This is a container. And this is what Eric gave big headaches. He did want to separate the world into containers and views. And now suddenly, when you are doing a transform on something, then depending on whether there's something as an R value or an L value, you either get a view or something that is really a container because it ships that vector around with it, right? And he didn't like that. He wanted to have a clear separation. Nice theory. We said we were more pragmatic in a way. We said, well, I don't care about the theory so much. I want the things that I write in my code to just work. And the way to do that was to just aggregate the vector into the transform. This is about the only thing that is different in semantics. There are syntactical differences. He likes the pipe notation and whatever. That's where you have you. I don't know if you've seen it. Like you do vertical bar filter, vertical bar transform, vertical bar la la la. He likes that. I don't like it because I say functions are functions. So if you have an input and you want to apply a function to it, then C++ tells us that this is a function. I don't want to reinvent function notation just for ranges. That was my opinion. If someone likes the bar notation, then maybe he also likes to write 3.0 bar sine bar cosine bar absolute. And I'm not opposed to it. If people want it, that's fine. And if there were actually proposals to do it in the standard library, in the standard language. But then we should do it everywhere. Should have a uniform approach and not have a special case for ranges where we can write the bars for ranges but don't write them anywhere else. That was why I don't like the bar notation. Then there is a similar, oh my God, the world is breaking down moment in building adapters. And I can try to explain it to you, and hopefully I can convey it. If you have a filter, first of all, if you have iterators, if you have purely iterators, so your filter range is implemented as two iterators. Actually, so if you have a filter iterator, then this filter iterator, which is iterating through your sequence, has to store the underlying end iterator. So when you're iterating and your filter iterator gets a plus, it's going to walk forward, right? Until it hits either what it is looking for, what it wants to filter, or it falls off the end. How do you know that you fell off the end? Well, you know because you carry around the end iterator with you. That means every filter iterator, if you implement it in this plain vanilla way, is containing the iterator itself and the end iterator. Now, when you then do of the filter iterator another filter on top, and then another filter on top, and another filter on top, and you do this 10 times, you have iterators that are 8 kilobyte in size, because you get a combinatorial explosion in the size of your iterators. That you can avoid. This is what I found. This is my little contribution to the standard, or to the proposal. I found this, and they changed it so that the iterators are only valid as long as the underlying range is valid. So that basically all the iterators can store a pointer to their range object. And the pointer to the range object is always just a single pointer. And there you get the end iterator from. So no matter how many stacks you make, your iterators, no matter how many stacks you make, the combinatorial explosion goes away, because the first filter iterator stores the actual iterator and a pointer to its range object. So while with me, you go one level up, you can do another filter, you get the 2 that you got from your underlying layer, they don't go away, and you get a third one, which is the pointer to your range object, your filter range object, which is different from the other range object. You filter twice now. And then you get 4 and 5 and 6 and 7 and 8 and 9. That for this to happen, to go from combinatorial combinatorial explosion or exponential explosion to linear, they had to require that the iterator is valid only as long as the underlying range is valid. And that Eric Niebler required in his proposal. That's good. The world is saved. Okay? So we went from exponential explosion to linear. Linear is still bad. I don't want linear. Okay? I don't want, when I pile this up 10 times, that I have iterators which are 10 words in size. So what do you do? Well, and this is basically where currently that's the state of the art of the Niebler proposal. We went one step further. We asked, okay, what can we do in order to get this away, to remove that additional linear growth in iterator size when you stack them, because we stack them a lot. And you can actually do something. The way to do it, and there's now a little bit hand waving, but it's really not that hard either, is you go away from the iterators. I'm not saying in terms of elements or borders, but you go away from the iterators in the sense that when you increment something or decrement or make an operation on the iterator, you always require the range to be supplied on which you're running. And so basically you don't have a iterator plus operation anymore, but you have a range increment this, and I call it index. This index, range increment index. And that's okay then, because you can now, when you now start stacking these ranges, the indices are basically always supplied the range with them, and the range then can go back down to its base range. Is that? So the increment, the iterator increment looks like you have a range increment iterator, say that for a filter range, okay? So what do? You go to your, this is a call on the range, and then you call the underlying range increment, the one below you, and ask it to increment its iterator. And that you can do by, but your iterator is still the original one from your original sequence. It's if I had a whiteboard, then it would be more easier. But end of the story is it's doable. It's doable. It's not very difficult. And the only thing that you have to do then is, in order to make this all interoperable with all this iterator stuff, you just basically wrap. An iterator wraps the index plus the pointer to its underlying range. So from the interface, it all stays the same. It's no difference, right? The only thing you're doing is you're wrapping this thing, but the implementation of the operations is not in your adapter stack. That's in terms of these indices. That there you have to do something different. But on top of it, it all looks the same. It's no difference in usage. But your adapters are just implemented in a different way, and then you can remove that complexity also. So these were the things that we did. And then what we also did for the ranges is we removed iterators. We have generator ranges. Generators are essentially things where you just call a function that enumerates. You call your range and you give it a functor. And the range enumerates its values into the functor, one after the other. It's really very, very simple. You turn the iteration is no longer external, like in the iterators, but internal. You turn it the other way around. You can't implement everything easily with that model. Many things where you have to freely iterate through your sequence don't work with that. But a for each can be implemented easily. I mean, that's basically all it does. There is an any of, all of. There are many functions where you don't need iterators. You only need a kind of an enumerator that spits out the elements. And what we wanted to do is to make this compatible with the regular algorithms. So you can use the same algorithms that you're using with all this iterator-based stuff with this generator-based stuff. So you can write an any of or a for each using these kind of ranges.
Why do you call them generators? What you tell is more like visitors.
Yes, I think the visitor is the other thing, right? What's the guy that you are visiting over? The visitor is the guy who walks around and is looking at things, and I'm visiting this, and I'm visiting that, and I'm visiting that. The generator, or the whatever you want to call it, is the thing that is being visited. Yes, it is the visitor pattern. But the nice thing is that you can use the same syntax that you use for your range-based stuff. So this is no different anymore. This was only really the idea. It's not a great thing, but it actually it turns out that you use iterators less and less during this model, with this model, and it can be also more efficient. I mean, if you're combining a transform with a filter, for example, the filter before the filter didn't really the way it's usually doing it is it's first checking whether the filter is accepting or not. And then it's again passing the value into your function or returning it as an iterator. So your plus in a filter adapter already needs to know the value. And then the the dereferencing again generates the value. So you generate the value twice if you have a filter adapter. And that you can avoid by turning this thing upside down, because then you're actually doing first generate the value, then you pass it into your filter, and if the filter says yes, you just pass on the same value further on. So you're saving actually a dereference. And if you're generating the value is very cheap, this is not a problem, obviously, to generate it twice. I mean, if it's just a pointer dereference, nothing's going to happen. But if this is something heavyweight, because you've got a big transform and there's some calculation going on and it's generating a value, then it actually may make a difference. You can. I can. Yes, you can. So you can increment or decrement borders. You can increment or decrement elements, as long as you're not overshooting at either end. But that's the same with iterators, kind of. So yeah. So you can do anything that you can do with iterators. The only thing you kind of cut off is that you don't allow dereferencing on borders, because it makes no sense, and you don't allow elements to go beyond end minus 1. So you cannot have an element at end, and you cannot dereference borders. These are really the two constraints that you are adding to iterators.
With borders and elements separated, what about invalidating those as a result of some operations on views or containers? Is it the same as
same problem? I would I probably wouldn't try to make any changes there, because this is highly technical stuff. This depends very much on your container, right? I mean, if your container invalidates its iterators, there's very little you can do. And trying to shield the user from these kind of details is probably bring about a big pessimization of your performance, because you have to write a different data structure in order to do that. I mean, and a vector works as a vector does, so I can't do much about it.
You said you use your library, and I would like to ask you, what is the business area of your application if you use this library?
We're shooting with big cannons at small birds. So we build an add-on for PowerPoint to efficiently do PowerPoint slides. And probably the cool thing we're doing is we want to do automated slide layout. So we want to be able to basically, you're plugging the elements on your slide together like Lego. You say, okay, this is on the left, and this is in the middle, and this is on the right, but you don't specify exactly where it should be. You just say, okay, this is aligned to that. And you can always delete things from the slide or add new stuff, and completely automatically, we want to basically re-layout the
Layout engine for PowerPoint.
if you will, layout engine for PowerPoint. Right. In C++, certainly in C++. No, you don't want to write ever. If you start writing an Office plugin, you would write it in C#, right? Don't.
Or even JavaScript. JavaScript.
Okay. JavaScript probably, maybe now. There are certain things you can't really do, but don't write it in C#. It's terrible. It's not compatible with Office. Because they are holding onto COM objects using garbage collected things. And the garbage collector never runs. And then they never free these COM objects. And C++ and PowerPoint, on the other hand, is written in a way that if you're holding on to to these COM objects, then it doesn't really work sometimes. So if you have a deleted, if your shape gets deleted and you're still holding on to the COM object, and you I can't get it together, but there is ways where you basically, because you're holding on to them, these zombies stay around. And you are getting zombies. You're pulling something out of the API and you get a zombie back. And you do calls on it and everything fails. And you are asking, why is that failing? And it only happens once in a while. And then it happens once in a while because some stupid C# add-in is still holding on in its garbage collector onto the COM object. And you know what you do then? Then you write an error mechanism that actually reaches into the garbage collector of C# and triggers a garbage collection. And then the problem goes away. So we run this problem, and then we say, oh, this fails. It's like, well, just free all the objects. Okay, run the garbage collector. And then the zombies go away, and then we restart. Don't write C# in object. Use C++ or JavaScript. That's a completely different world. But yes, not C#. Yes. It's sugar. It's purely sugar.